Thanks, Dinu, for inviting me to be here. It's a great pleasure to speak in this a nice place. So today I'm going to talk about the construction of the mirror space. Can you see this board? So as you all may know, the mirror symmetry is about duality between two different geometries. So one side you have symplectic geometry, and on the other side you have the complex geometry. And the main question that I want to discuss today is how to construct the mirror space. And I'll start from a single Lagrangian, or deformation theory of single Lagrangian, that is supposed to give a local chart of the mirror. And then I want to explain how to patch them together for a Glover mirror. So let's start with the deformation theory of the Lagrangian, or deformation of Lagrangian. So let me begin with the most well-known mirror construction due to SYZ, Strominger, Yao, Jaslow. So this is saying that if you have a symplectic manifold or Kähler manifold with a Lagrangian torus fibration, so the fiber is Lagrangian torus, half-dimensional torus, and then in this case the mirror space should be obtained as a dual torus fibration of this guy. Just X check and then T check. So if you closely look into this T check, then T check is nothing but the collection of T itself together with certain local system, C star, not C star, U1 local system. And if you bury this torus fiber on the mirror side, then the X check is nothing but a complexified deformation space, deformation space of a Lagrangian torus T here. Complexified deformation space of T. So this is the slogan of today. So no matter what, the mirror space should be obtained as a certain kind of deformation space of Lagrangian. And then we need to look for a local chart of this X check. So I'm not going to use the whole fibration, but alternatively, we fix one Lagrangian. Fix one Lagrangian. This one Lagrangian in X. So in fact, it doesn't need to be a torus. So you just fix some Lagrangian. So in later application, this will be either a torus or a immerse Lagrangian, immerse S2 in fact. So you fix one Lagrangian and study the deformation of this single Lagrangian, but not geometric deformation, but something called formal deformation. Of this Lagrangian L. So what do I mean by this formal deformation? By the way, this is supposedly giving you a local chart of X check around this L. So what is this formal deformation? All right, so formal deformation is the following. So you look at floor complex and you transform the A infinite structure on this floor complex. That's what I mean by formal deformation. So more precisely, if you have degree 1 elements in Lagrangian floor complex of this particular Lagrangian L, then this B, so this which is of degree 1, deforms the A infinite structure MK on this Lagrangian floor complex. So this is due to Fukuya and Ota Ono. It's hard to remember the order. And so what's happening is before deformation, the MK structure on this guy is nothing but counting holomorphic disk with the following configuration. So this is holomorphic disk that bounds L. And then, for example, if you have inputs, x1, x2, or xk, and then you look at the image of these points, or image that this point sweeps out. So this is my evaluation. This is mk of x1 through xk. But now, if you have this B of degree 1, then you can deform this structure by inserting more markings here and there. So after deforming by B, what you're looking at is still the holomorphic disk that bounds L. And also you have these inputs, so 1 and then this evaluation. But now you allow these edges to intersect a lot of bits, arbitrarily many bits. These are all bits. And they proved that this new kind of discounting gives a well-defined infinite structure on this guy. So this is what I mean by deformation or formal deformation of Lagrangian. But of course, we're not looking at arbitrary B, because we want this object to be still meaningful in chi category after deforming by this B. So for this to be the case, you have to solve the following equation. So for L to be meaningful, or L comma B to be meaningful. So L comma B is kind of a deformed object in the chi category. So at least you should be able to define floor cohomology of this guy. So for this to be the case, you should impose the following condition. So M1B is M2BB plus da should be either 0 in Z graded case, and some constant that depends on B times unit in Z2 graded case. So this is something called Maurer-Cattan equation. And if you just forget this part, then this looks pretty much like a deformation of complex structure. This is like differential, and this is bracket. But now we're in this infinite world. So you have to put all these higher operations here. So this is something called Maurer-Cattan equation. Maurer-Cattan equation. And I'm going to denote by MCL the space of all solutions like that satisfy this equation. So B that's satisfying this condition star. And this MCL will serve as a local chart of my meter. So to give you some more concrete feeling, I do a very simple example, which is just pair of pens. All right, so the example 1. So I have this pair of pens, which is a 3-puncture sphere. Then I'll take my Lagrangian to be a certain immersed S1 that looks like the following. This is immersed S1 with 3 self-intersections. And this was considered in Seidel's Genus 2 paper. And also, we studied this Lagrangian to prove homological mirror symmetry for compactification of pair of pens. But anyway, there is this Lagrangian, which I denote by L. And then I'll use this immerse generator here. So there are 3 self-intersections. Let's call this guy X, Y, and Z. And then my B. So can you see this board? Yeah, the B. My B will be a linear combination of the 3 self-intersections, XX, YY, ZZ. And then I want to do something like this, like deforming an infinite structure and so on. But then, as I said, we have to impose that condition star, or Maurer-Cattan equation. But in this case, B is actually Maurer-Cattan, meaning B solves that equation for any number XYZ, for any XYZ in C star, not C star in C. So why is it the case? Because there is a reflection symmetry. So let me try to just compute that equation star. So if you compute this guy, star, then a priori you might think there is this M2 contribution, like M2 of XY is this guy and so on. But if you look at more closely, then there is a triangle on the backside. So they're M2 to cancel with each other, and you're only left with M3. And then M3 is easy, right? M3 is this triangle XYZ. So what you get is XYZ times the unit of this Lagrangian. And in fact, this potential XYZ, or this W XYZ, is called superpotential, and this is an LG mirror of this pair of pens. So the W equals XYZ. They're mirrored to each other. So this pair of pens has this LG mirror. And in what sense? I call it a mirror of pair of pens, is because, of course, if they are mirrored to each other, you expect the chi category of this guy has some relation with the matrix factorization of this guy, W. So let's just take one random Lagrangian, for example, this. And you see that this split my XYZ triangle into two pieces. One is this, and the other is this. And then one guy has this X corner, and the other one has YZ corner. So this Lagrangian L is mirrored to the following matrix factorization: X times YZ equals W. So this is in here, this is in here. So they're mirrored to each other. And so experts might have noticed already. So this is simply computing M1B. So L, you take the Floer complex between L, and I computed M1 deformed by this B. Then that will give you this matrix factorization, one by one matrix factorization. And actually, you can complete this as an infinite functor. So what I proved with my collaborators, Zhou and Lao. So in fact, this correspondence, let's say just F. So F can be made into an infinite functor. And this is always the case. Whenever you have L and you turn on some deformation or Maurus-Cartan deformation, then you always have some infinite functor from chi category to matrix factorization category. Or in Z-graded case, this should be replaced by dV co of MCL. Okay. This is my first example, and let's move on to a slightly more complicated one. Right, because we're using a canonical model. So H0 just consists of units. All right, so example number 2. So this is my favorite conifold example. So let's look at the following non-compact threefold. This is U1, V1, U2, V2. So this is in C4. And I take additional variable Z from Cx. Then I want this phi variable to satisfy U1, V1 equals C minus A for generic number A and B. So what is this guy? So in fact, Z is a redundant variable. So if you rewrite everything, then this is just deformed conifold. This is U1, V1 minus U2, V2 equals epsilon for some suitable epsilon. But I now take a puncture for this Z. So this is, in fact, this minus some divisor D. So this is more or less a deformed conifold. And then I look at this Z projection, which is actually a double conic vibration. The arrow is too low. Then the generic points, over a generic point in Z plane, so this is my Z plane, over a generic point in Z plane, you have T star S1 times T star S1 from this equals constant and this equals constant. So you have this guy. But there are two singular fibers. One is over A, the other is over B. So, and types of singularities are slightly different. So over A, you have singular times smooth, regular. And over B, you have smooth times singular. So this is the double conic vibration structure of this guy, a deformed conifold, and I took a puncture here, Z equals 0. And then, all right. And then if you draw this straight line here, then this is actually, so lying over this line segment is S3. So you take the fiber product of two vanishing symbols from here and from here over this line segment, and that is exactly S3. So let me just draw it this way. So you have S3 here. Lagrangian S3, Lagrangian S3. This is Lagrangian. So let's call this guy L1. This is Lagrangian S3. And I can take another one, which has non-trivial winding number around 0. like this. Your picture is not very good. But this is, by the same reason, this is also Lagrangian 3-sphere, and I'll call it L2. And then I'll set my L to be a union of L1 and L2, which can be thought of as immersed Lagrangian. It's L1 plus L2. This is kind of immersed Lagrangian. And again, I want to do this kind of formal deformation. So a kind of deformation parameter I can use here. So from the C plane picture, you can see this is still white. 4 different angles or 4 different corners like this. I have 3 corners here to deform the floor theory. I have 4 different angles here. One is, let me be careful about the x. Let's say x and y, and this is C. This is W. So in fact, if you choose some suitable gradings on L1 and L2, this x, y, z, w. So both, all of them are of degree 1. And then I'll take B to be the linear combination of this. But then you need to be slightly more careful in this situation, because I take two different Lagrangians. So this is not really irreducible. So in this case, these variables x, y, z, w are taken from certain quiver that records the composability of my morphisms x, y, z, and w. So x, y, z, w are actually the elements of the following path algebra of the quiver. So you have 2 arrows. So maybe this vertex kind of represents to L1. This is 2. And then you have 2 arrows in both of directions. And this is x. And so x is going from L2, I think L1 to L2. And z is also going from L1 to L2. So I put x and z here, and y and w here. This is my quiver Q. And this x, y, z, w were taken from the path algebra of this quiver Q. So this is simply just keeping track of when you can compose these morphisms x, y, z, and w. Okay, right now it's just formal. And then you again solve this equation, Maurer-Cattan equation, the star. I give star. So this one, you just solve this one. And in this case, I think only M3 survives. So this is also M3. But note that this is actually a graded setting. So you shouldn't expect this to be a something times unit because of degree reason. And I want this to be 0. But this is in fact computed by Chan, Pomeliano, and Ueda. And this is, for example, you see x, y, z minus z, y, x, and w bar, some degree 2 elements here, and so on. So now, if you want this guy, this star, to be 0, then there's a simple solution. Just declare this coefficients here to be 0. So that gives me some relations in this path algebra, quiver algebra. So you have, this is not capital, sorry, z, y, x. You have one relation, you can see here, and then you have 3 others, which are cyclic permutation of this guy. So let me not write down, because we have 3 more. And this is actually partial derivatives of the following cyclic potential. W, z, y, x. This is partial derivatives. So this quiver with this relation, or ideal generated by these relations, is called a non-commutative Crepin resolution of conifold. So this whole thing together is non-commutative Crepin resolution of conifold. So again, this fits into a usual mirror symmetry situation. So on one side, I deformed or I smoothed out the conifold singularity. And although this is non-commutative, but on this side, on the mirror side, you get resolution of the same singularity. All right. Yeah. So then the question is, okay, so if you don't like this non-commutative mirror or this quiver things, And then the question is how do you get commutative mirror of this guy, or commutative resolution of this coniform. And then you see that if I choose more than one Lagrangian branches here, then you always get quiver, because each vertex represents one Lagrangian components. So I should choose one single Lagrangian, but in this case, it's not enough. So you need to choose several single Lagrangians. And then there comes a gluing. So each gives you a chart, and then still commutative, and I'll glue them all together to get a commutative mirror of this deformed coniform. Okay. Yeah. I can just erase it. So what do I mean by gluing, or how to glue the charts? Gluing. Here comes the gluings of chart MCLs. Okay, so the idea is the following. So the rough idea is, for example, if you have one Lagrangian L, so this is the space of formal deformation for L, and you take another Lagrangian, L prime. So this consists of B prime, and this consists of B. And then you have two different local chart of the mirror. Then how do you glue these two? So which information should allow us to glue these two? So that's the question. So you pick one point here. So pick one point here. And that actually represents the Lagrangian, which is boundary deformed by B. Pick another one here. It's, I think, too small. LB. Take another one here, B prime. This is L prime deformed by B prime. Now the question is when to glue these two, or when to identify these two different objects in the chi category. And so the question is when to identify these two. Now we are so we're in the chi category, right? So the most natural way to identify these two is to find an isomorphism between these two objects in the chi category. So the answer, or kind of rough answer, is when there's an isomorphism, alpha from, let's say, LB to L prime B prime in the chi category. Here, isomorphism means you also have a map from L prime to L, which composes with alpha to give identity, and on the other way around too. So this is really like categorical isomorphism. Or in fact, we should weaken the condition a little bit because we're in a homotopy world. Let me not mention this. So this is more or less isomorphism you see in the category. All right. So and then we're going to glue this to object. And this is not totally abstract nonsense, because when you glue these two charts using this isomorphism, then you can still have a functor. So this is again Cho and myself and Lau. That in this case, the statement is slightly slopey, but I'll give you a more concrete example in a minute. So there still exists a functor from the chi category to a homotopy fiber product of homotopy fiber product of the category that comes from MCL, and the one comes from coming from MCL prime. How do I call it? Fiber product of corresponding B-side categories. B-side categories. So today I'm more into construction of the mirror itself, so I'm not going to talk about this direction that much. But anyway, if you have this gluing, then automatically you have this functor as well. That hopefully establishes an homological mirror symmetry in good cases. But anyway, let's focus on mirror construction itself more for today. Precise All right, let's. Yeah. So it's not good. So
Like, what are the objects? What are
yeah, sure. I'm going to do that. So here we've got category of X. Let's say both MCL and MCL prime produce some LG model. So you have function W here, and W prime here as well. And then on this side, you have two different DG category. One is MCW prime, and the other is MFW, W and W prime. And I want to take the fiber product of this guy, but not exactly the fiber product, but some sort of homotopy version. So here you have to put some intersection overlap region 1. And of this guy, this fiber product category is 3 different things.
Actually, I was asking, what are the objects in chi category?
Just general, any Lagrangian, any Lagrangian.
Compact or non-compact? Exact?
All right. In my example, it's always compact. In the examples I'm going to deal with today, they're all compact.
The L's are compact.
L's are compact.
But over here they weren't, right?
In this example, right? Here. You're talking about this one.
So the L's are compact.
Yeah, so there are like 2 different situations here because I'm looking at something C2 graded. So this is kind of very sloppy statement. So this is C2 graded setting.
Okay, so the L's are
so if you go to a Z graded setting, like non-compact Lagrangian and so on, and then I need to switch everything to DB co, and then probably I can do a replica category here as well.
No, but I just want to understand what you mean. So L's are compact Lagrangian grains?
Yeah.
Not necessarily exact or anything?
Yeah, it depends on setting, but probably in these statements, I want to keep this setting of usual like FO style category, compact and spin and relatively spin.
But, I mean, do they have to be unobstructed or something? Or
Yeah, unobstructed, of course, unobstructed. So this is sort of Yoneda embedding. So as long as Floer complex makes sense, you can always do this procedure. Because here I'm just going to take the Floer complex of my L, between my L and L. And here I'm going to take Floer complex of my L prime and L. So as long as these 2 make sense, I can do this procedure. So probably I should say, all right, so my setting is whenever this Floer complex or Floer cohomology makes sense, or this A infinite structure makes sense.
So for your definition of chi, you also have M0 in this case, right?
Yep.
So then do you fix the value of M0?
Yeah, sure. So if you have a value of M0 to be lambda here, then I think you need to fix this to be W minus lambda and so on. All right. So let's go back to non-compact situation again, which is okay. All right. So again, the example is the. So before doing this example, I'll give you a somewhat simpler, with just two-dimensional conic vibration. So so the same picture, but now the general fiber is just conic, one-dimensional conic, and I have one singularity here, over which we have this guy, this singular conic. And then, for example, Oru used this kind of picture and produce some torus vibration that admits one singular fiber here. So if you look at this circle, then you should imagine there is one circle, which is actually the 0 section of this T star S1, lying over every points of this concentric circle. So that sweeps over the whole space, and this gives you a Lagrangian torus vibration. But there's one singular fiber, which is this immersed S2. Yeah, this is immersed S2. So if I attach all this S1 to every point, then this collapses to a point over this singularity. So this is this is the simplest Lagrangian torus vibration that admits a singular fiber. And then, in fact, this reveals some interesting geometry, something called wall crossing. So in fact, if you choose Lagrangian torus, which is inside this singular fiber, and you choose another one, which is much bigger, which is outside this is singular torus fiber, and then the disk moduli or floor theory of these two Lagrangians are quite different. And I'm not going to talk about it much in detail, but the reason being that when you go from here to here, you actually have additional disk contribution, which is this guy. This is actually a holomorphic disk that bounds Lagrangian lying over this circle. And then the disk moduli is kind of jumping when you move from here to here. So this is called wall crossing. And Oru will analyze it and just write down explicit wall crossing formula. So the question is whether we can recover this using the theory I'm talking about today. So there's this wall crossing. Wall crossing. Yeah. Then there's immediate problem here. Because, OK, so I'm going to use L1 here and L2 here. And then, or L here and L prime here. And trying to glue two Markov-Cartan space. But the thing is, because I need this, where is it? Isomorphism to glue the Markov-Cartan space. But in fact, in this situation, this L and L prime never talk to each other because they just don't even intersect with each other. So this lemma D is to make them intersect artificially. Okay, so let's do that. So instead of using unused torus fibers in this picture, I'm going to choose slightly different ones. So the same situation as before. So one singular conic, and the origin is removed. And I'll choose one like this, and the other one like this. So in fact, the isotopy type of, okay, I'm going to maybe I'll put tilde here so that I can keep L and L prime for this. So from L tilde to L, or L prime tilde to L prime, I don't actually change the disk moduli that much. So I'm not touching the singularity, for example. So so these are almost the same, or floor theory of L and L prime are very similar to L tilde and L tilde prime. But now they intersect, right? So and you can talk about like whether there is an isomorphism between these two objects, and if there is one, and how do we glue MCL and MCL prime. So I need first to deform, or I need to explain how to deform L and L prime. So in this case, I'm going to deform L and L prime by local system. So I'm going to deform this by LZ. Well, you can think of it as some element from H1, but in this case, it's much more explicit. Let me show you how to do this. So I'm going to equip L with some certain local system called Z. So what's happening is this picture correct? I think yeah, let me choose some other notations to match with my notes. This is L1 and this is L2, and this is C prime. Sorry about this. Yeah. So what do I mean by the C and Z prime? Simply as follows. So for example, you choose some point here. This point means the circle lying over this point. As I said, you have this conic fiberation. And over here, you can choose zero section of T star as 1. So this point actually means that circle, which is a codimension 1 subtorus of this L1. And then when you count the holomorphic disk, okay, I have to put C2 here. When you count the holomorphic disk, when the boundary pass through this points, then you just multiply Z2 to this counting. So this is the one specific representative of local system, or C star flat connection. So this is actually Z1, Z2. Now do the same for L2. So maybe you can just choose this one. It doesn't really matter which point we choose, so they're all like equivalent. But just to get the standard formula of the wall crossing. So I'll choose this points. And again, I fix the direction. So again, when you have a disk And if the boundary of the disk passed through this circle here, you just simply multiply the corresponding number here and there, depending on like orientation of the intersection of the boundary and the circle. And all right, so this is Z2, my description of Z2. So where is Z1? So if you look at here, then in fact these two Lagrangians intersect along S1. So this is clean intersection. But if you don't like, I can perturb one of this to get transversal intersection, but at two different points. So if you look at here, then in fact the L1 and L2 both give the zero section of the cotangent bundle in the conic fiber. But maybe I can just perturb one of them like this, and just keep the other one. So you see two different intersections. And if I zoom in here, then this is exactly the same picture. And then I put so one is L, or fiber of L over that point, and fiber of L2 over the same point. And maybe I can just do the same thing here. Z1 and Z2. Sorry, Z1 prime. It's the other way around, right? Z1 prime. So I choose this specific representative of my local system Z and Z prime. So this is how I deform L1 and L2. And then you see that you have C star 2 worth of this kind of deformation, because I'm just putting a C star flat connection or C star flat line bundle here. So the MC L1 and MC, or just Li, is both C star 2. Good. And according to this scheme over there, I need to look for isomorphism between L1, Z and L2, Z prime. And then I have two intersections here, and two other intersections here, but only one of them is degree 1. It depends on how you draw. Let's just fix this guy to be alpha. And alpha is the unique degree 0 intersection. Oh, sorry, so the isomorphism must be degree 0 to have an inverse of the same degree. So this is always degree 0. So there's unique degree 0, 1 elements between in the floor complex between L1 and L2. And for this to be an isomorphism, you first require that this alpha is closed under M1, Z, and Z prime. So it should survive in the floor cohomology. Otherwise, this homotopically 0, right? So I should first compute or check whether so alpha is in CF 0, L1, Z, and L1, L2, Z prime. So again, this Z and Z prime just means you just put this weights when you count the holomorphic disks. And I want to compute this guy, which I hope to be a 0 for alpha to be an isomorphism. Right, how to compute this? And there are two different contributions. So of course, you need to find count the holomorphic strip between L1 and L2. So so one pairs is actually can be seen from this picture. So if you project this down, then this will occupy. So there are two strips or three strips, one occupying this region and two occupying this region. So one here and two here. So roughly speaking, there are two because one is above the what's this over this guy? It's like this, and one strip is above the singularity, and the other strip is below the singularity. So okay, let's first count this contribution. So here I have no decoration due to my specific choice of flat connection. So this guy is just counted as 1. But here, as I said, I have 2. And first one is really a Z2, which is counterclockwise. This is counterclockwise. So first one is Z2. So I'm not talking about the sign. Z2, I'll not talk about the sign. Z2 prime inverse. So this is the holonomy along the strip. And the other one, which is above the wall, or above these points, has different homology class. The boundary of above one has one more wrapping along the fiber direction. So you have the same plus this additional factor, which is C1. And then this goes to beta here. So this is the base, or those contributions that can be seen in the base. But also you have fiber-wise contribution, which is this. So you see two pairs, alpha bar and alpha. But because of this choice, one is just counted as 1, and the other is counted with this corresponding weight, which is C1 times C1 prime inverse. So the other one is 1 minus C1 and C1 prime inverse, and alpha bar. And I want this to be 0, because I want my alpha to survive in the floor cohomology. Then this imposes certain relation among all these variables. So first, if you look at this guy, then this means C1 prime should be Z1. And the base direction, so you have, I think, if you compute all these things and then arrange everything in a nice way, then this is the same as C2 prime equals C2 and 1 plus C1, which is the standard wall crossing formula. So and then under this condition, you can actually check that alpha is an isomorphism. So in fact, beta here, seen as a morphism in the other direction, can serve as a inverse of alpha. So this alpha is really an isomorphism. So you can. This is something you have to check by computing. So yeah. So now I can kind of glue these two patches together to have this space. Two C star 2 together glues along certain region using these equations. So what is this? Oh, by the way, the same idea already appeared in one of Seidel's lecture notes. And also the Pascal F and Tonkanok use this idea to study wall crossing from some monotone Lagrangians. So Pascal F. All right. So what is this space? I have C star two of C star 2, and then glue them using these relations. So maybe I want to keep this words. So this space is pretty simple. In fact, yeah, I'll just show you. So the mirror description. So for example, MCL, which is isomorphic to C star 2, has the following 5 relation structure. So you have Z1 comma Z2, and you project this to a Z1. And of course, Z1 equals 0 is missing. So this is Z1 equals 0, because flat connection should have a non-zero holonomy. And genetic fiber is again C star, which is the space of Z2. This is C star. So I'm describing MCL, which is C star 2. So I'm just looking at Z1 projection. But over, all right, so I think this is just trivial fiberation, right? So every fibers are T star S1. But for some reason, let me draw the fiber over -1 in the following way. This is what I want. So this is, because I'm removing these points. So this point is missing. This is still C star. So for some reason, let me draw this trivial Z1 fiberation in this way. And then MCL prime is also C star. And again, you look at Z1 prime projection. And again, the genetic fiber, general fiber is G star 1. Every fibers are T star S1. But something over -1, I draw in this way. And then I'm gluing this to C star 2. Where is that? Using this coordinate change. So you glue these two. Maybe let's call this guy star. And there's star. And what you get is, if you look at the first equation or second, then you see that anyway, you see that all these fibers, which I draw in a normal way, they just identify with each other. So they just identify with each other. So this is C1 equals Z1 prime plane. And then you just have the same one here, because they're exactly identified. I think by the second relation, so unless C1 is -1, that gives identification between Z2 and Z2 prime. So other fibers are fine. They're just simply overlapped with each other. But this one is more interesting. So when they glue these two, they're actually outside the gluing region. So what's happening is what you get is this. So you have C star 2 kind of glued in this way. But you never know what is in this point. So this point is still missing. If you glue C star 2 only, 2 C star 2s only. This is the gluing. This is the, so this point is missing. This point is missing. In fact, you don't know whether there is only a point or P1, P2, whatever. Can't be P2, right? So anyway, something is missing here. Of course, we expect to fill this out by something, and for that reason, I need to use the immersed Lagrangian or singular torus fiber. So how do I find this? Missing points. So take the immersed S2 like this. So this is immersed S2. And then, as I did in, I haven't done this, right? Did I have? Anyway. Yeah, as right, I think I did something similar here. So as I have done here, I choose two immersed generators. One is going from here to here, and here to here. So U and V. Let's call this guy U and V. So this is my new Lagrangian L0. And then to this glue chart or glue space, I throw in the additional chart coming from this immersed Lagrangian S2, which is boundary deformed by these immersed generators, U and V. So yeah, I think I don't have enough time, so let me just say U, U, and V, V is actually Marokatan. This solves the Marokatan equation. And for L0. And yeah, let me keep, so in fact, there is some issue here. So because if you do this kind of deformation, and there's some constant this contribution from here. So you cannot really guarantee the convergence issue. So for to do this precisely, you should work over Novikov ring. But let me just pretend that we can do this over C. So first of all, this is Marokatan. So the charts coming from L0 is just C2. In fact, very small bore around the origin because of the convergence issue I mentioned. And then this point can be recovered by the point is actually U equals V equals 0. So I'll write down one coordinate change from, let's say, L1 to L0. This following C1 equals, this is again by computation, which is similar to what I have done before. Z2 is U and UV inverse. So this is the coordinate change between MC L0 and MC L1. And the funny thing is, not very funny, so this Z2, if you look at this equation, so Z2 is C star. But now, if you move onto the right-hand side, the U is an immersed variable. So U can be 0. So U can be 0, and this actually fill out this point. All right. So this is what's going on. And then, as I promised, I came back to this deformed conifold example and try to show you how to get the commutative meter in quick minutes. Which color would be nice? Maybe purple. Yeah. So right now you're here. So this is pretty much the same as a previous example, although this one is two-dimensional. But if you look at locally here, for example, and you see that this is actually the previous example times T star S1 here. So just locally here, you just reduce everything to the previous example by taking some sort of reduction by this S1 action here. So you do the wall crossing or this kind of gluing business locally here, and you do this once again here. So in this case, you have to do this wall crossing twice. But yeah, so it's really locally because you don't have global S1 action like this. So anyway, I can do this here, and there are some compatibility. So what you get is, all right, so applying is this not visible? Applying this gluing to this deformed conical example, what you get is exactly resolved conical. Although I don't have time to describe it in terms of coordinates, but this is actually resolved conical. And in fact, this also coincides with the SYZ mirror construction. So, so why do I emphasize this missing point a lot? Well, this is just one point, right? So why should I care? This missing one point is missing, and there's a reason. Because eventually I want to study the some specific example, the Crossmanian. Maybe I can just erase this. Okay, let's move to the last example. Is Crossmanian 2-4. CR. So this is the space of this is over C, space of complex two planes in C4, and probably this is 4-dimensional, and there is this Marsh and Ritz, So they use some re-theoretical method to construct a mirror of this. I'm not really expert to that, but anyway, there's some construction, not from Floer theory, from some other one, to get the meter X check and W check. Which is actually a Landau-Ginzburg meter, and this is usually called Ritz mirror. This is called Ritz mirror. It's a Ritz mirror. Anyway, so the goal is to the full mirror. In fact, okay, so let me tell you some story about this. So there is a work by some Japanese people, Nishino, Nohara, Ueda, which partially recovers this mirror in the following way. So they looked at some sort of Lagrangian vibration. So there is a vibration called Galpan-Setlin. So in fact, there are several of this. Like, I think they call it like generalized Galpan-Setlin system or something. And I'm not going to describe this vibration. But anyway, this vibration is different from toric vibration. So for example, the non-generic fiber could be S3 cross S1. So this is called Galpan-Setlin. Setlin. And as I said, generic fiber is T4. It's 4-dimensional manifold, T4. And then those people, Nishino, Nohara, and Ueda. Sorry. So they use a toric degeneration technique to compute the mirror potential for this T4. So this is toric degeneration. And they get something, some LG model, let's say X check and W. So the reason why I put this under bar here is because this is strictly bigger than this guy. And even worse is, in fact, W check has more critical points than this guy. So some critical points are missing. Critical points are missing here. So by recovering the full mirror, I meant to recover this missing critical point. All right. So how do I do that? Maybe we can keep this. So so the generic fiber is T4, and then there's something missing. So the natural thought is, okay, why not using other fibers? So for example, not for example, so I think all the non-generic fiber in this specific example is S3 cross S1. So S3 S1, S3 cross S1 fiber. And they are Lagrangian as well. So in fact, this, if you look, the B is a polytope. The base of Galois-Setlin system is a polytope. And this S3 cross S1 is lying over the edge, facet. And is that right? Either edge or facet. I think edge, yeah. And then if you go to this toric degeneration, then this S3 part is collapsed into points, and you get S1, just like toric. So over edge, you should have something lower dimensional torus, right? So I'll show you some more precise picture. So let's just use this as one of our Lagrangian. So and then what you do is, so I'm simply taking this guy as the analog of where's my picture? I just erased it, of this the immersed Lagrangian I talked about before. So okay, I'll just show you the picture. So yeah. So what I'm going to do is first I'm going to remove some divisor, and then I take the S1 reduction here. And this is exactly recovers this picture. So yeah, just to convince you, so this is deformed conical. So why is this the case? For example, you can use Plucker embedding. So for example, you have this embedding from X. My X is GL24, sorry. So there's this Plucker embedding into P5. And then X, I think probably 2. Yeah, this is just hypersurface in this case, right? And then one Plucker, the Plucker relation. So this variety is cut out by one relation, C12, Z34, G13, C24 plus C14, C3 is 0. So now what you do is to remove the divisor where, for example, Z23 is 0, and then take the S1 reduction. Then you will lose these coordinates, but this is still homogeneous coordinates. So if you divide everything by Z14, then what you get is exactly deformed conifold. So this is one way to see it. So this guy is deformed conifold.
So D is not an anti-canonical divisor?
No. So D is probably a union of this guy, in this picture, this guy, and one in the infinity. So yeah, let me just redraw the same one. So what's going on is, okay, so as I said, this is the deformed conifold. And like here, you have S3 here. So the fibration in this reduction picture is the following. So you have a lot of T2. I think probably need to look at this. Okay, let me just be sloppy here. You have this torus fibration, which collapses into F3. So this is the typical shape of this Galois-Setlin fiber. And then I'll choose, not this guy, but I'll choose this guy. I think probably you need to choose one of this, probably this. This one. And then as before, use this. So this is immersed S2 cross S1. And again, you have 2 degree 1 elements from this immersed generator. One is U and one is B. And you do the same thing as the one that I did before, which I erased. So in this case, UU and VV is also Maurer-Cartan by the same reason. And U equals V equals 0. Okay, so let me slow down a little bit. So this is my L tilde, and I choose L0 to be this guy, L tilde, times S1, which is a Lagrangian in the total space, X. And then I turn on this boundary deformation, or Maurer-Cartan elements, which is U and V, and I have additional S1 direction here. So I should turn on one more C-star flag connection along this direction. And then, in fact, 0, 0, some number. I actually don't remember the number. So there are 2 of them, Zi. So these are some specific number, I equals 1, 2. So this actually recovers the missing critical points here. So this, first of all, construct the mirror something like this by gluing method. And then that immersed Lagrangian or immerse Lagrangian S2 cross S2, right? No, T2. Immerse S2 cross, this is immerse S2 cross S1 and S1. So immerse S2 cross T2. So you use all this together to glue and get this LG meter, big LG meter, and that's particular points recovers the missing critical points between these two. So this recovers the missing critical point. And maybe one last remark is, in fact, all right, so you can try to do with the higher n, or you can try to use the same arguments for quadrics, because this is kind of quadratic relation. So this is looking at quadrics in a way in Pn. But if n is higher, then you need to analyze T star Sn. But here I'm basically looking at T star S2. I'm just using immerse S2 product with some trivial vectors. But if you go to higher dimension, then for example, you have to analyze the floor theory of immerse S3 or S4 and so on. So yeah, I think we're working on it now. All right, thank you very much.